Okay, welcome to the lab. And again, we'll get started here in just a minute or two. And we're just going to go over, again, the lab that's open just now and the one for today, basically, and sort of this week as well, that we're starting on, which is the redox experiment. So we'll just give it another second or two and we'll get going on talking about that. Again, if you have any questions, feel free to type them in and I'll answer them for you. And just give me a second here. I'm just going to stop sharing the screen for just a sec to go look at something just to verify before we get started talking. Okay, I'll be with you in just one second, just taking a look at one last thing. Okay. All right, and that worked. Okay, so for today's lab, which has just been posted, is basically the oxidation reduction experiment. Now, for this particular experiment, there was normally three parts. There's part one, two, and three. We're going to do part three, so it's not even posted up there. I don't think you should be able to see it at all. So we're just going to do part one and part two of the experiment. A reminder as well that make sure that you do follow the online experiment. Yeah. So again, they took a lot of these experiments and they certified it obviously for online. So if you sort of follow, what's in perhaps your lab manual, it may not be perfectly the same and stuff like that. So I don't think you'll run into maybe too much problems with this experiment. But again, as we saw, for example, with the buffer experiment and that type of stuff, just make sure that you follow kind of what it says online, what's available, and stuff like that. Although in this experiment, I don't believe there's any type of simulation or anything like that that you'll need to do. So, like I said, I don't think you'll run into any sort of problems, maybe like some of you did with the buffer one in terms of some reagents not being available. Um, so we're going to look at part one and part two is basically what we're going to do in this experiment. Part one, pretty much what they did is, and what you'll see is basically they took a 24 well plate and they took a bunch of metals there. So they had, I think, copper, zinc, and magnesium. And basically, you're just going to kind of take the spot plate and do a number of reactions with it. For example, HCl, I think zinc sulfate, and so forth, magnesium nitrate, and there's a few others, obviously, as well. When you look at it, you'll be able to see it. So really, sort of part one, again, like I think I mentioned last week, and again, they used to do sort of this experiment, I think, in Chem 50 as well. But basically, what we're looking at is really single replacement reactions here, right? And we're looking at single replacement reactions, which has this general sort of formula where we take something, and in this case, it's going to be something like a metal and an ionic compound that's positive and negative. And if the reaction takes place, A would come in and kick out the positive guy because it's a metal, right? It will doesn't have a charge, but it will become positively charged. So at the beginning, it has no charge, but will become positively charged. So it'll kick out the positive guy there and make a new ionic compound, A and C. So in order for it to really in this example, A needs to be more reactive than when it's replaced. Obviously, if it's less reactive, then the reaction wouldn't take place, and obviously you wouldn't get an overall reaction that occurs. So I believe, if I'm not mistaken, there's perhaps a video of some of the reactions, maybe some photos as well, where they sort of added all these things and sort of videotaped it as well. So you'll be able to kind of watch that in the procedure that's online and obviously make your observations. So for each of these parts, part one and part two, I believe there will be a kind of notebook page, if you will, that you could use. So either like a PDF version of it or kind of like a Word version where you can, again, like you would in your regular notebook, watch what's going on, write down observations, and I think there may be some other questions involved as well that you may have to answer on there. And then also for each part, in addition to sort of the notebook pages, I'll call them like the data analysis pages, if you will. I think they're pretty much what those were. They're sort of the data analysis, I won't say really calculations, but in this case, you're going to have to do a lot of sort of balancing equations and oxidation states and writing sort of these redox reactions. So they're basically going to do all these reactions. So for example, if we took something like zinc and we reacted with hydrochloric acid, again, this reaction, if it did take place, the oxidation state of zinc here is going to be 0. Remember, any metal that's uncombined in its natural state will have an oxidation state of 0. Hydrochloric acid really is a positive, right? H plus and negative. So if this reaction took place, the zinc would come in and kick out the hydrogen. And when it does, hydrogen comes out by itself, and hydrogen's natural form when it's uncombined is hydrogen gas, right? So you would see bubbles sort of happen in this sort of experiment. Then the zinc, which has a +2 charge, would hook up with the chloride that has a -1 charge and make zinc chloride, right? And with you there in front of the HCl, I think that's sort of it in terms of balancing. Now, if we look at this equation, and this is some of the things that you'll have to do sort of for the post-labage, I don't want to say post-lab, but I guess more the data analysis part and all that, where there's those questions, is that they're going to ask you to kind of write at some point the net ionic equation. And sometimes people, when they think about net ionic equations, they sort of always think double displacement reactions, right? But a single replacement reaction really is in that big category of redox reactions, right? It's really a redox reaction that's occurring. So we can write a net ionic equation for a single replacement reaction, and it kind of works the same way as like what you would do with a double displacement reaction. So if we take this reaction. I'm just going to rewrite it first. We could actually, again, figure out what's going on here. Oxidation state of our zinc, 0. Oxidation state of our hydrogen, +1. Our chloride, -1. Oxidation state of hydrogen in its natural state is 0. Oxidation state of the zinc over here is +2. And again, our chloride is -1. So basically what's happening, if we sort of break this apart like we would a sort of total ionic equation, is you could go through it. You would keep this guy together. You would end up with, so kind of like what you do with your double displacement reaction. If you do the side of the equation, you will also find your spectator ions. And then any questions on that so far? So this would represent really the net ionic equation that's happening in this particular basically single replacement reaction. Now, if we look at our net ionic equation a little closer, we could also break it down a little further. So let's get a fresh page here. So we had zinc plus a couple of these guys. Made this and that, right? So we can write our half reactions as well, right? Our half reaction for our oxidation. Again, it's our zinc going from 0 to +2. So we would have our zinc going to zinc with a +2 charge and our 2 electrons. Again, electrons on the product side here, as it's an oxidation, they're being given off. And electrons on our charge. So a couple of other things that we can identify as well from this, and what I'll do is I'll get rid of those crossed out so we can kind of see them. I'll just get rid of that, get rid of that. When we look at this, the other things that we can identify is the stuff that we talked about as well. We can identify, in addition to what's being oxidized and what's being reduced, we can identify what is our oxidizing agent and our reducing agent. And in this case, our reducing agent would be this guy, right? So again, you're going to probably be asked for all these things. You have to write the net ionic equation, which you may be able to break off into its 2 reactions, which as you can see is there as well, each of those. And obviously be able to identify what's being oxidized, what's being reduced, and also the reducing agent and the oxidizing agent. And also along the way, obviously be able to identify. Any questions on sort of how to, or any part of that? And really, if I remember correctly, it may also ask you to perhaps make an activity series, right? So I'm trying to, then will not replace anything that is higher on the list. So since all these are, I think in part 1, pretty much single replacement reactions, it may ask you at the end to kind of put it in order in terms of activity series. Or it may ask you to put in order based on oxidizing agent or reducing agent. So I'm just trying to remember off the top of my head, and I don't remember perfectly. And again, they might have changed it a little bit from what's in what we usually do, but sometimes they'll have you put it in order based on oxidizing agent or reducing agent. So when you're trying to determine, which one is perhaps a better oxidizing agent or a better reducing agent, you want to look at each of those metals, for example, and try to determine, how many times it went through oxidation. So for example, just hypothetically speaking, not probably what you're going to see. Let's just say zinc went through oxidation 4 times and magnesium went through oxidation twice. Because zinc would have went through oxidation, say 4 times versus twice, the zinc would be a better reducing agent than the magnesium, and vice versa, for the oxidizing agent. So based on your observations in part 1, you're going to want to kind of look and see okay, this guy went through an oxidation reaction this many times. This one went through it this many, and you could kind of put them in order. So I almost tend to think perhaps they have you put it in order based on either reducing agent or oxidizing agent. That's essentially part one's experiment. Any questions on that? And again, you will have basically just papers to fill out. So what's up there again for part one is some notebook pages where you again can make some observations and some other things. And then again, I call it kind of the data analysis page, but I don't know if it's really called that online, but where you'll kind of do sort of this stuff here, write out some equations, some net ionic equations, figuring out some oxidation states, who got oxidized, who got reduced, and all that kind of stuff. Any questions on part one of the experiment? Okay, so then let's talk about sort of part two of the experiment. And in part two of the experiment, again, it's sort of set up the same way in part two in terms of what information you need to sort of fill out and that type of stuff. So again, there'll be, I believe, carbon pages, notebook type pages that you can kind of fill in. And then again, after that for part two, there will be pretty much data analysis pages that again, you can do some things. So we're going to look at the effect of pH on redox reactions. So the first thing that you'll kind of see when you go to part two of the experiment is you'll see this big sort of table. And this big table will have like a whole bunch of things in it. You know, say like MnO4 minus. You'll come across this table typically have this color or this type of precipitate. So, for example, descriptions of each of these sort of species. And you're going to use this table to help you when you sort of are watching. Again, it's either going to be a video or a combination of video and pictures of these reactions sort of taking place, but to help you sort of decide, okay, I saw something that went from purple to something that went to green. So that must mean what I got going on is this in terms of my half reaction, right? You know, so this is my reactant, this is my product, and again, you could look at something like this and figure out one of your half reactions. Now, I believe a couple on that sheet there, the sulfate and the sulfite. When you do look at those are both colorless. Yeah. So in terms of their sort of description. So obviously colorless is not going to be super helpful when you're trying to determine, did I see something change with it? So what you do know though, right, in all these reactions, they're redox reactions, which means if you have an oxidation, right, you should then have a reduction. So for example, here, if I did this reaction, you would know that, sulfite to sulfate or sulfate to sulfite. And what you would really be looking for is evidence of a reaction like from this part. So let's just say we did this purple, right, and green. So if you saw this evidence here that the thing went from pineapple was sulfate, then you know that the sulfate and the sulfite basically took place, and that would be your other half reaction. So there will be some in part two where you add, let me see which one you add here, if I can find it. Um, So you are adding, for example, I think in part 2, you're actually adding, I have this flipped, you're adding sulfite. So this would be sort of one of your reagents, for example, and let's just say you added MnO4 minus. You're going to add it with some other stuff as well, but these are sort of your 2 reagents that occurred. Again, you're only going to be able to kind of see the color change occurring for the Mn. But if you do see a color change occur for the Mn, that means that this guy went from our sulfite to our sulfate. So even though you can't kind of visually see that because they're both colorless, you know that if the Mn did go through, say, a reduction, that the sulfate had to go through, say, the oxidation part of it. That sort of makes sense there. And again, here, basically, right, this going from, this is -2, 6, that's like a +4-ish, right? And then over here, I'll let you figure that out, but it is going through an oxidation as well. So in the part where you add sulfite, if you saw some type of reaction occur, then you know that the other part of your half reaction is going to be the sulfite going to sulfate. So in part 2, you're going to be mixing these guys, and I'm going to not do all the oxidation states for you because actually that's part of the table you need to fill in. And so it's going to ask you in this table to correctly identify all the oxidation states. So I'll stop with the oxidation states so you can at least have something to do other than copy what I wrote here. But we're going to do, for example, let's just say in part 2, you mixed MnO4 minus, and you mixed it again with the sulfite, right? The other thing that you're going to see is in certain parts, they will add HCl into the mix, and certain parts, they will add sodium hydroxide into the mix as well. So in addition to, say, these 2 things, you're also adding in either HCl or sodium hydroxide. And again, just for that made up one, which I'm not even sure is the one you would maybe do, I think it was that, we'll say we saw this reaction occur. So when they mix this and we saw here, you will either add HCl or sodium hydroxide. So what is the purpose of sort of adding those things to the mix? So we're going to see the effect of sort of oxidation and reduction in acid conditions and also basic conditions. And at some point, what you'll have to do for ones where you do see a reaction take place is you'll have to write the balanced redox equation for it. Now, the balanced redox, so if you saw a reaction occur in the one that added HCl, when you're done, you'll need to use 2 things to sort of help you figure out what's going on. You'll need to use that big table and your observations that you saw, like we did here. Oh, I saw it go from purple to green. So obviously purple, this is what I started with. Green, this is what I ended with. By the way, what you start with, you'll know because it'll tell you the actual substance that you're adding. So you'll be able to find it here. And like I said, if I added sulfite as the other guy, I know that these 2 guys are involved together. Again, won't always be sulfite involved, but when it is, that's it. That will give you your start of your 2 half reactions. Then you need to go through all those steps that we talked about balancing these redox reactions in acidic solution or basic solution. So again, if we were to do this, we would balance everything other than oxygen and hydrogen, which is the same. In this case, we would need to add water to whichever side needs oxygen, which you don't. In this case, we would need a water over here, right? A couple of H pluses over here. Then you need to add your electrons and all those steps that we talked about at the beginning of this chapter. So in part 2, when you go to balance these redox equations, you're going to need to balance them as in either acidic or basic conditions. And that's going to be really determined on whether or not they added, again, HCl or they added sodium hydroxide. Any questions on that there? So what you'll see is they added a couple of drops of sodium hydroxide, or they added a couple of drops of HCl into the reaction mixture, And again, really, for most of the purpose here, you'll be able to figure out that tells you it's acidic conditions or basic conditions. And that's going to be really important when you go to balance these redox reactions. So part two, not too bad either. Again, you're basically going to be looking at some observations. You're going to use that table to figure out, what species are present. And then you're going to have to, in part two, based on whether or not you added HCl or you added sodium hydroxide, um, as to whether you need to balance these redox reactions in acidic or basic conditions, which again is going to require you to add waters, add the H pluses like we talked about, add the electrons, add them back together. In addition, in part two, they'll probably ask you some things like in part one, what is being oxidized, what's being reduced. You'll have to figure out some oxidation states of everybody, perhaps some reducing agents and oxidizing agents as well. Any questions on part two? So again, it should be pretty straightforward. And like I mentioned, we're not going to do part three. We wouldn't have done it in person either. So we're just going to do part one and part two. And I think that'll be some good practice about balancing these guys and, figuring out oxidation states and balancing their oxidation half reaction, redox half reaction, and all those kind of things. Again, a reminder that the report for this will not be any type of formal report. It's essentially, I think there's four things basically. It's essentially the notebook pages for each of the parts, part one and two, that's up there, filled in obviously, and then obviously, again, I don't recall off the top of my head what they called it, but it's like basically kind of like the data analysis part for part one and two. When you do these, all I ask is you could do them kind of neatly. Yeah. These things can get messy very, very quickly. So whatever you decide to turn in at the end, hopefully all of it, obviously, can you just make sure it's kind of organized and neat as well. I believe in addition to those two parts, there should be some pre-lab questions. And I'm trying to think if there's some post-lab questions. I'm not sure there is or not. I don't think there is. I'll double check, but I don't think there is. So I think you'll need the pre-lab questions. Again, part one and part two is basically two parts, and that will be it. So I think it's going to be due sometime in the end of next week, maybe next Thursday or something at night at 5. So you got like almost 2 weeks to do it. That should be probably plenty of time. And I'm imagining on Thursday, we'll talk about the next experiment, which is the electrochemistry one, which is basically the galvanic cells. And that will probably be available towards the end of this week as well on Thursday. Any questions on any of that? Again, everything should be posted up there, so you should be able to go and work on it. And again, if you have questions, I'll be happy to answer them. And again, I don't think there's any type of simulation or anything like that that you have to do for these, so it should be pretty straightforward, I think. And a reminder, please make sure that you do follow what's online. Again, this one may be very similar to what's in your lab manual, but again, they might have changed certain things. So just make sure you do follow what's online and go based off of the procedure and all that kind of stuff that's on there. Any questions on any of that stuff? Okay, so what I'm going to do though, just to kind of preserve it so I don't have to do a bunch of editing and stuff like that, I'm going to end this lab meeting right now. So I'll have just this sort of introduction to the experiment so I could post it later up online. And then maybe I'll take like a 15-minute break or so, and then I'll open this back up. And again, if you want to go start working on it, or if you have questions on that or anything else, again, I'll be here to answer those questions. Sound good? Any questions on anything? Okay. So again, it's 12:20, so about 12:35, I'm going to reopen this. And again, for any questions, if not, then obviously it should be up on Canvas right now. The experiment, you should go start working on that. Yes. Okay.